Welcome to your example video for Chapter 13, Lecture 2. We are looking at time-dependent oscillation equation and relationships, and I'll start our discussion with page 33. This question is from June 19 Paper 42. So as you can see, this is the same spring mass system that we discussed in our lecture. Please watch the lecture if you have not yet watched. Okay, and you are given the variation of the length of the spring plotted against time. Okay, it's important to note that we didn't start from zero. The equilibrium position is actually midway between maximum and minimum, because the spring will always have length. Does that make sense? Okay, so this is the equilibrium position. Your amplitude here is 2.5 and negative 2.5. Alright, so once we identify the equilibrium position, we can easily tell what the amplitude is. Okay, and with that, we can now answer at which time is the speed maximum. All the yellow points that I highlight is where speed is maximum. Why? Because it's equilibrium position. So any of this time lah, you choose one lah, whichever you like. Okay. Maximum elastic potential energy, which means the spring is either maximum compression or maximum extension. So you could take all the point on top, you could take all the point below. You like lah, just write your favorite number lah. Okay. Let's say I take 0.2. You can put all of this as well. These are all options. Cool. All right, very easy. Moving on. Determine omega. Omega is 2 pi over t. From here, we can easily tell t is 0.4 second. So for you to solve or unlock all the things in simple harmonic motion, you need to know omega, you need to know maximum displacement or amplitude. Once you have these two numbers, whatever they want you to find, you can just go like, come at me, bro. I can solve all the questions. What you want? Kinetic energy, maximum acceleration. I know everything. So this is unlocking the level. So if you want to find Vmax, this will be A omega. So taking omega, which is 15.7, and the amplitude is 2.5 cm. Please remember to convert to SI because you can see this is meter per second unit. Alright, so this will be 3.93 meter per second. Maximum acceleration A omega square law. Note the operation. Whenever we go one level maximum from displacement to velocity to acceleration, we multiply by omega times omega times omega. So to find maximum acceleration, we will take A omega square, which is just this number square lah, and then you will get 6.17 meter per second. So easy, huh? Like that, 4 mark liao leh. No, wait, more than 4 marks, guys. 6 marks. I need to pause here. The impact is not enough. Let me pause again. This thing is 6 marks, the whole entirety of it. Do not let go of the oscillation question because this is a bonus chapter. 讲了啊, tell you it's simple harmonic motion lah. Everything here is simple, okay? Anyway, we're going to move on to part C. In fact, I think this 8 marks is bonus. Anyway, now we add another spring. Explain the change, if any, in the period of oscillation of the mass. So if you got 2 spring, it's harder to stretch. Harder to stretch means the spring constant is doubled. So this is the first point that you can write. The spring constant is doubled. And this means that the period of oscillation decreases. How you know, miss? Nah, remember in lecture 1 I derived the equation. But miss, 我不记得, I don't remember the equation. T is 2 pi square root of m over k. Now if you don't remember this, because I proved already, you don't remember, then maybe use a bit of logic. You got logic or not? I believe in you, you have one. You should have. Think about it. Your spring system is more stiff. Okay, so because it is more stiff, right, the restoring force is greater. The force to pull the mass back is greater because you are talking about a stiffer spring. So the acceleration is greater, then the movement is faster, period will decrease. Make sense? Alright, moving on. By reference to displacement, what is meant by simple harmonic motion? So this one is pretty straightforward liao lor. Acceleration of a system is directly proportional to displacement from a fixed point. Acceleration and displacement are in opposite direction. So please write these 2 points for full marks in definition. Okay, So here you can see that you are asked to give two reasons why the motion is not simple harmonic. One, we have discussed this before, but one, the graph is not a straight line through the origin. Don't forget to mention origin as well. And number two, the maximum displacement is not the same. You can see the maximum displacement here is like one big box. Then the maximum displacement here is like 1.5 big box. So cannot log. Okay? So it must be like a symmetrical graph. So you have this thing bobbing up and down. And one thing you notice is that the amplitude is decreasing. Now when the amplitude is decreasing, this means that the oscillation is losing energy. It's bobbing up and down, then it's bobbing less and less. So it's losing energy. So if it's losing energy, this means that there is this thing called damping. Now I have not discussed damping. It is the last lecture in this topic. But damping is a loss of energy in the oscillation. So you can see that the amplitude is decreasing. But the frequency is maintained, because the period is the same. So when you're asked to find the angular frequency omega, we will once again employ our beautiful 2 pi over t. You can tell that the period is 0.8 throughout the oscillation, so you get 7.85 radian per second. Maximum acceleration, a omega square. Alright, so you need to find maximum displacement, the largest possible amplitude, because they want maximum acceleration. Okay, so multiply by omega square. That will give you 0.924 meter per second square. Alright, so now our block has a mass of 120 gram. Oscillation of the blocks is damp. Damp here means losing energy. Calculate the loss in energy of oscillation of the block during the first 3 complete periods of its oscillation. We know that the total energy is half m a square omega square, but the amplitude will change, right? So when t is equal to 0, the total energy will be half ma square omega square. I can just calculate. I got the mass, convert to kilogram. The amplitude, maximum amplitude is 15 cm, and the omega is 7.85 square. So doing this, I can calculate the energy, which will be this amount. And then I will take 3 cycles. Now 3 cycles later would be this point, 2.4. This looks like 0.9. Okay, refer to the graph. So from here, you can repeat the calculation after 3 periods. Your total energy would be half m a square omega square. New amplitude is 9 cm, sorry, 0.9 cm, and omega is still the same because the period is still the same. Substituting this will give you this value, and if you want to find energy loss, subtracting those values. Don't let them take your last mark, Lord. Forget to minus, very sad, right? Okay, so after subtracting, you will get this value. Very easy. If you know the equation, you know what and when to use. And the final question that we'll discuss in this example is a bit earlier. This is in page 9, May June 12, paper 4.1. Okay, so this one you're given a simple pendulum, and the displacement of the pendulum is expressed in this cosine graph because the timing starts at maximum displacement. Okay, can be sine, can be cosine. This is what I meant. Use the data to determine the horizontal acceleration of the ball at the displacement x is equal to 2 cm. So don't forget the equation that defines simple harmonic motion. A is equal to negative omega square x. So we can find omega. Omega is 2 pi over t. So look at the graph. What is our t? 0.6. Substitute inside. The displacement is 2 cm. Ta-da! So if they ask you to find acceleration and they give you displacement, it's a bonus question. Alright, so we substitute using the calculator. And then we will get the value of 2.19. I'm going to pause here to highlight that this thing is 3 marks. 3 marks for using a very simple equation. Don't let it slide. This chapter is easy. Okay, one last thing. Where is the 3 mark, right? 1 mark is the answer. 1 mark is a substitute, knowing how to code this equation. A is negative omega square x, and substituting omega as 2 pi over t. The 3rd mark is when you substitute the correct numbers inside the equation. Alright, finally, you are asked to sketch the kinetic energy against time graph. Is it a sine square graph? Is it a cos square graph? Miss, how to know? Memorize. No need lah. You look at this one. This is a displacement time graph, and you can see from here that x is equal to cos. Okay lah, nicely it's 4. 4 cos omega t. Okay, and omega is 2 pi over 0.6. Note that this is that important. So this is 10 pi over 3. So if you actually want to write the complete equation for this graph, right, you can call this omega as 10 pi over 3. But to find V, I will differentiate cos, in which I will get negative sign. So because it's sine omega t, right? So this one must be sine square. Okay? Or you can look at this graph lah. Here, maximum displacement ma, so the kinetic energy should be 0. Here is the fastest ma. So all these blue points is where the kinetic energy is 0. So I'm going to plot out all these blue points here. Okay, 0, 0.3, 0.6, and 0.9. Okay, all these blue color highlighted points are where the kinetic energy is 0 because it's at the highest or lowest, no, they're at the highest left and right position of the pendulum. Okay, all the green points where the graph is the steepest is where the kinetic energy is maximum. So I'm going to plot out all the green points. They're actually the midpoint between 0 and 0.3. That will be 0.7, no wait, 0.15, 0.45, and 0.75. Okay, so now we can just smoothly join them in a sine square curve. Okay, so sketching out this graph will also give you 3 marks. Okay, correct shape, correct values, and correct cycle and correct period. Okay, so before I move on, I would like to caution you, if this graph is given, the period of this oscillation is not 0.3, it's 0.6. Because in one oscillation, you will manage to pass through the equilibrium position 2 times. Think about it. If you have a pendulum, you swing to the left, you swing to the right, you pass the equilibrium position 1 time, 2 times. Okay, passing it 2 times meaning the period would be 0.6. Alright, so the correct cycling is 1 mark, shape is 1 mark, maximum at EK is the other mark. So that's all for this. I think I will write out the mark scheme for you. 1 mark is the sine square shape. All the values is positive. And also at the same time, we have the peak at EK, and your energy is 0 at T equals 0. And your period, this period, if you look at the mark scheme, right, this so-called period is the shape period, not the period of the oscillation. So whenever you're asked to find period of the oscillation, that would be 0.6. Okay, but the period of this shape would be 0.3. So having all these 3 correct will give you 3 marks. And please try task 2 now. And I will see you in lecture 3. Bye-bye.